This video will talk about combining functions together, particularly the idea of a composite function, the idea of f of g of x. What is going on when you're looking at questions like this, and why all of a sudden are like the domain and range questions suddenly way harder than normal, right? Like normally domain and range is some of our easiest stuff, but in a combined function, domain and range is actually pretty complicated and difficult to understand. Let's just begin by reminding ourselves what a composite function is. So remember, you have x, which is something like a variable, right? You sub x into the function g of x, it produces an output, and then that gets subbed into f of x, right? So let's say f of g of x, just so we can see it like this, right? So I've given a question before, for example, where x represents a person's age, and then g represents the person's height at that age, and then f represents the person's speed based on their height. So when you do a combined function, it's as if you are taking an input, you're putting it into an intermediary, and then you're putting that into the final function. So what we're often doing in these situations is that we are creating a function that goes all the way from the beginning to the end. Let me give you a better example. The one from the lesson there is a good one. It talks about the radius of a sphere, right? So like it says the radius, so you're rolling a snowball or whatever, and the radius of the snowball depends on time and is equal to 2t, right? So basically the idea was after 1 minute your radius is 2, after 2 minutes it's 4, after 3 minutes it's 6, etc., etc. Then we also know that the volume of a sphere is based on its radius, and it's equal to 4/3 pi r cubed. So if r is a function of t and v is a function of r, then the combined function v of r of t is asking the question, how do you go from time to volume? Now, of course, what we're doing in this situation is we're doing time, which tells us radius, which tells us volume, right? And if you like, this is the r of t function, and this is the v of r function. In many ways, what we're trying to do is create a single function, v of t, that takes the whole thing and does all the instructions at once. It's kind of like, imagine you had directions to get to the grocery store, and the first set of your directions got you to the train tracks, and the second set of directions got you from the train tracks to the grocery store. I mean, you could just combine all the instructions together and do one function or one set of instructions instead of two, right? And this is kind of the idea behind this stuff. You have a function inside another function. So any of these questions where you've got something inside something else, try to think about it. I always like to draw these diagrams where you have a variable, you have the inside function, and then you have the outside function. And if you can try to think about it like this, hopefully that helps, right? Where you consider like a function inside another function. Now, what makes these particularly tough is their domain and their range. Their domain is hard and their range is really hard. So in terms of like the kinds of questions, like let's look at a couple of examples. I really think, I think this is one of the places where the the lessons that we're doing are offering like pretty tough questions. Like I don't think my questions will be very different from these ones. Like even something like this number 1 is quite challenging when you break it down. I mean, of course it makes sense, and once you understand it, it's not so bad. But of course, like trying to brute force your way through it and understand it in the first place is pretty difficult. So let's think of a few basic examples before we go and talk about the examples that they gave. Let's talk about some of our parent functions. So consider functions we've studied so far. We have root x, we have log x. Let's just say it's log 10. We have let's say 2 to the x. We have exponentials, and we have sine. Let's stick with I guess we could do like polynomials, but I don't think we necessarily need polynomials. I think we should be able to make most of our case with these. So let's do some experimenting with putting them together and just seeing how we can use what we know to try to answer a question like the one from the one from the book here, which is, I think, you know, a tougher question than I think this one's like probably about as like this is like a good thinking one. Maybe a variation of it. We can look at a couple. Anyway, let's just look at our basic functions for a sec. So root x, as we know, so maybe make this a little easier if I just make a little more room for them here. Sorry, I know I just changed the order. All right. So let's take a look at these ones for a sec. We can look at their domain, we can look at their range. Now root x, we know, has a domain of x greater than or equal to 0, and it has a range of y greater than equal to 0. Log has a domain of just greater than 0, not equal to, right, because it has an asymptote at 0, but it has a range of all values. 2 to the x has a domain of all values, but it has a range of only positive numbers. And sine x has a domain of whatever you want, and it has a range of 1 less than equal to y. Negative 1 less than equal to 1 less than equal to y. Let's also just throw in x squared and x cubed, just so we have them. So again, they're polynomials, right? They never have a restriction in the domain. But this one has a restriction in the range, y greater equal to 0, whereas this one has no restrictions. Okay. Now, when you try to understand a function's domain, okay, here's how you do the domain of a composite. Domain of composite. Okay, and let's stipulate that f is the outer function and g is the inner function. So here are the rules. So number 1, g of x's restrictions stay. Okay, and you think about why. Well, x has to go into g of x, and then g of x has to go into f. So obviously, if x isn't in the domain of g, the whole thing breaks down immediately. It's like you can't even do the first step. So you have to keep g's restrictions, the inner function's restrictions. The second set of restrictions are f's restrictions, f's restrictions, but you have to set them to g. Okay, now try and figure out, let's try and use an example of like why this would work. So let's try, just as an example here, let's put sine on the inside. Sine on the inside and root x on the outside. Okay, so here's an example. What would happen if we put sine on the inside, root x on the outside? Now, sine has no restrictions. Right? So you think about the f is the outer function, g is the inner function, right? So g is sine x. Now, if I look through my little domain checklist over here, I see that clearly g's restrictions stay. Okay, well, g doesn't have any restrictions. Its x belongs to real numbers. But then it says f's restrictions set to g. Okay, now f does have restrictions, right? Normally for f, you would say x greater than equal to 0. So here's the trick. You don't say x greater than equal to 0. You say g of x greater than or equal to 0. That's the key. Because g of x is the variable inside f. So if f has restrictions, those restrictions need to be observed by g, not by x. Let me show you what this graph looks like, because to specify, right, let's keep it to one period here. We know that sine does something like this, right? And it's positive for the first little bit and negative for the second little bit. But look at the restrictions in my function. G of x has to be positive. That means whatever is about to get drawn, it should exist over here, but it shouldn't exist over here. Because when x goes into sine and comes out as a negative, that negative can't go into the square root. Okay, so let's see what this looks like as an example. if we draw it. Okay, so I'm going to draw a square root of sine x. Now, interestingly, the graph, let's just show, we'll just switch it to radians quickly just so you can see. What do we do? Pi over 2, I guess. You can see that my graph exists, no problem, between 0 and pi, but it does not exist between pi and 2 pi. You should be able to explain why not. I think this question's maybe not quite the one I would ask, but I think it's really good for demonstrating why there's a problem here, right? Because sine doesn't have restrictions. In fact, root x is supposed to restrict us for any negative number, but you can see there's all kinds of negative numbers that work in this function, even though the original parent function of square root x doesn't exist over there. Because remember, x is not going into square root. Sine x is going into square root. And wherever sine x is positive, this will exist. Wherever it's negative, it will not exist. We could apply the same logic by looking at log, right? Because log has basically the same restriction. If we go log 10x, right? Let's just hide this for a second. You can see that log 10x exists, right, everywhere that's positive. But log 10 of sine x doesn't, right? It like the other one, it only exists between 0 and pi, because that is the place where sine is giving us a positive number, and that positive number can go into log. Right? You see what's happening? So you really have to break this one down and think it through very carefully. Where does the first function exist? Where does the second function exist? Now, the range is actually an even bigger challenge, but maybe let's stick to the domain for a little bit longer, and then we can make some comparisons. So let's try another option. Let's imagine we were doing square root of 2 to the x. Now, in this case, x is going into 2 to the x, and then that is going into square root. So, think it through. Square root can only accept positives, only accept positive values. But 2 to the x, if we look at 2 to the x, its range is only positive numbers. So that means any x can go into 2 to the x, and any result of 2 to the x, any y value, is allowed to go into into the square root function, unlike the one we were just doing with sine. So if I go back here and I replace this with square root of 2 to the power of x, right? We shouldn't see any breaks in this graph at all, because there are no values that give it any trouble, right? It's like all the x's can go into 2 to the x. They all come out as a positive number, and that positive number is allowed to go into, so I just want to remove this radian so we don't need it anymore. And those positive numbers can go into the square root function. Okay? Now, by the same, so this is a really, really important idea about the domain of a composite function. It's very difficult to intuit this. You really have to process it and think about it more deeply, right? You need to find the restrictions on the inside function, and then you need to find when does the inside function violate the outside function's restrictions. Let me do one more example that I think is about as difficult as I would ask. Okay, so I'm going to set the outside function to log, let's say log 2x, and I'm going to set the inside function to x squared take away 4. Okay? Now, go through your checklist. Number 1, g of x restrictions. Well, g of x is a polynomial, and we know that every polynomial, without exception, has a domain of all real numbers. So there are no restrictions so far. That's step 1. Step 2, f's restrictions. Sorry, I keep making a apostrophe. Sorry. If you've taken calculus, you'll know why I keep doing that. It's a different notation. F of x restrictions restrictions set to g. Okay, now f of x does have some restrictions, right? F of x can only accept values greater than 0, except what we're going to do is we're going to say g of x has to be greater than 0, not x. Remember, x has to go through g first before it gets to f, so it's not that x has to be positive, it's that whatever comes out of g of x has to be positive. So let's do this. Let's solve this inequality. Replace g of x with this, right? And solve the inequality. Now we know how to solve the inequality. You've let one side be 0 and factor the other side. So x minus 2 and x plus 2 greater than 0. And that tells us on our number line that there's an issue at negative 2 and there's an issue at positive 2. Now if you think about this, this is an upward opening parabola that would be positive over here and positive over there, but negative in between, right? And you sort of have to think about what this graph looks like. It goes down 4 and, looks something like that, right? And so it's negative in this region, but it's positive in these regions. This means that the answer to our question in terms of this domain ought to be this area and this area, but not that area. So x is less than negative 2 or x is greater than 2. That's what I'm expecting the domain of this function to be. So let's test. So x squared minus 4 is my inside function. I believe I called it, I think I called it, and it doesn't really matter, but let's be thorough. And then f of x is log 2x. All right. So those are our two functions. You can see that the log doesn't exist over here, and the quadratic doesn't exist down here, right? But if we put them together, f of g of x, right, we get something kind of bizarre. It exists after 2, and it exists before negative 2, but it doesn't exist in the middle. There is no way to explain this, right, or intuit this, or like memorize this. The only way to understand this is to understand what is happening to your variable and why your variable, right, is not allowed to exist in the middle of this equation where the quadratic would give you a negative, because that negative cannot turn around and go into the log. Okay, so super important idea. With that done, let's try to address some of the questions from the page. So let's take like this first one. It says f of x is a linear function and g of x is a square root. State the domain of and range, so it's asking for the range too, I can talk about that as well. The domain and range of f of g of x. Alright, so the inside function is g of x, and it has a root 3x plus 1. Okay, that is the inside function. Now you know that the inside function must be the case that whatever's under the bracket, right, whatever's under the root must be bigger than or equal to 0, and thus x must be bigger than or equal to negative 1/3. Okay, this is the step 1 of your domain. Remember, it's always a two-step process. Find the domain of the inside function, and you have to keep that restriction. So that restriction is good. Okay, we're keeping that. Now, step 2 is to take f, right, f of x's domain, and set it to g. Now, easily, or good for us, there is no restriction of f here. So g, therefore, g of x is allowed to be anything, right? It can be any value. There are no restrictions. So when I draw this one, the only restriction I'm expecting is the one that came from the inside function. So let's just quickly show. Okay, so f of x is negative 2x minus 8. G of x is the square root of 3x plus 1. And if I do f of g of x, what happens is I get a function here that you can see exists only after x equals negative 1/3. So x equals negative 1/3 is right there. And you can see my function only exists on the right side of it. Okay? Now, the range of this thing, it really takes some concentration to understand. Okay? So what we want to understand about the range, and there's a couple of sort of tricks we can use to this, but there's not really a reliable strategy that always works. Okay? For the range, what I'm going to do is I'm going to point out that the outside function is decreasing. And how do I know that? Is because, like, look at it. It's a line with a negative slope. That means it is always falling, right? As x gets bigger, this function gets smaller. And again, just to go back, like, we can take a look at it. It's pretty obvious. It has a negative slope. It's always dropping. So when we think about its range, okay, its range is always, its y values are always getting lower. Okay, so the further we go to the right, the lower the y value goes. Now, our function, the inside function, right, has a max or a min value. Okay, so this is what I want to analyze. So the inside function. So does the inside function have, a max or min? Okay, now in our situation, the inside function is a square root that starts at negative 1/3 and rises up. Okay, so I'm going to do my best. This is a really complicated idea. Every value on my root is getting bigger and bigger and bigger. Remember, x goes into the square root function, and then that goes into the linear function. The linear function is always dropping. That means that the bigger I go on my square root, the lower down my other function is going to be. It also means that the lowest value, so again, let's just say it like this, the lowest value on your root is equal to the highest value on your decreasing function. And you got to think about decreasing to understand that, right? It's like, if my root function never gets lower than 0, then 0 has to be the highest value that my decreasing function is ever going to get. Now, on the other hand, if my root had a highest value, right, then that would be my lowest value on my decreasing function. Okay, so try to understand a decreasing function. The farther I go, the lower it gets, right? The lower I go, the higher it gets. So let's see if this makes sense. My root has a lowest possible value at negative 1/3, 0. That is the lowest value that my root function ever has. So this corresponding point must be the highest possible value on my other graph. Let's verify that. Okay, so negative 1/3 goes into my function of g, and of course it comes out as a 0. Because I get 3 times negative 1/3, which is negative 1, plus 1 is 0. Then I put 0 into the other function, negative 2x minus 8, and I come up with the value negative 8. And so my hypothesis is that 0, negative 8 should be the highest value that f of g of x can hit. Okay, that should be the highest value it can hit. Now, let's go back and check. If I type this in, right, you see that, okay, we got the domain, right? We know the domain was at x equals negative 1/3, right? But the range should be at y equals negative 8. And true enough, right, I can find that spot. So this is, again, it is not easy to do. It really takes a lot of thinking to do these ones. And, again, you might expect like one of them, maybe like a multiple choice version and then a do-it-yourself version. And I honestly think like this question is about as hard as they're going to get. Maybe let's just experiment and see if there's like another one here that would be good to do just while we're together. I don't think 2 is like super tough. Like if you want to ask on the forum, I can probably go through 2. Let's just see. I thought there was another one where. Yeah, let's do this one, right? Let's do this one with the quadratic and the exponential. I really think like I suppose I could ask this one, but I really think this one is pretty tough. I think it's probably fine. Yeah, this cos one is good too. You know what? I kind of went through this one on the forum already, so let me do the cos one instead. So let's tackle this cos one. All right. So here, let's zoom in. Zoom in and we'll try again. All right, so let's try and go through our same logic, okay? So f of g of x. Now, this one, the domain, okay, well, whatever. Let's answer it and then we can comment on it after. So f, of course, is 2 cos x plus 9. And g, yeah, so this is f. And then g is 5x minus 40. Sorry, I'm just going to zoom in a little bit further so my writing is hopefully a bit better. And we're doing f of g of x. So remember, domain, two-step problem. Okay, domain is a two-step problem. Number 1, you analyze g's domain. Number 2, f domain set to g. That's your two-step problem. Okay, so look at g of x. It's a linear function. It has x is any value, y is any value. Nothing I can do about that. So are there any restrictions to record? No. When I look at the outside function, which is 2 cos x plus 9, it has, again, no restrictions in its domain. It's sinusoidal. Right? Sinusoidal, which is x is any real number. So when you think about this one, the inside function has no restrictions. The outside function has no restrictions. Therefore, the combined function cannot have any restrictions. Right? Where would they come from? Right? They could only come from restrictions on one of the two functions that make it up. So let's try and tackle the range now. The problem with this one is that cos x plus 9 is not a function that always rises or always falls, right? It's not an always increasing or always decreasing function. And we know that cos x, when you think about cos x plus 9, I mean, what would that look like? Well, it would have a axis up here at 9, and then it would have an amplitude of 2, right? Though it could go 2 higher or 2 lower. Right? As long as the x values go through a complete cycle, right, then there's no reason why this cos function will not reach its own max and its own min. And indeed, if you just think about this like this, if you actually like put them together, right, this is just like a regular cos question where we put a 5 and then x minus 8 and then plus 9. What is this thing's amplitude is 2 up and 2 down, and its axis is at 9. So this function should be able to go anywhere from 7, right, up until 11. That would be my guess for its range, right? Y is any real number between 7 and 11, including 7 and 11, right? So let's look at this one. And then, I think that should, well, let's see if there's anything left to talk about. So for this one, okay, f of x is equal to 2 cos x plus 9. G of x is equal to 5x minus 40. And we're drawing f of g of x, which you can see here. And again, what are we looking at? No restrictions in the domain whatsoever. Y is limited by 7, and y is limited by 11, right? Y has to be in between those two values. There's no other option there. Let's try the more difficult version of the question, which is, what if it asked for g of f of x? Right? What if it asked for like the other order, right? So put f inside and g outside. Okay, now let's try and go through and use our tools here. Now once again, f is the inside function, and f's domain is any value. So nothing to do there. Secondly, you take f of x. I got this reversed. Here, right? We take the outside function and set it equal to the inside function. Set the domain equal. But of course, the domain in this situation is any real number. So once again, this isn't going to change. It's still the fact that the range, the domain is any value. However, the range, okay, look at the outside function, g of x. It is always rising, increasing, right? This function is always increasing, okay, because it's 5x take away 40. It's a straight line with a positive slope. Now that means that when we think about the function 2 cos x plus 9, right? Sorry, not the plus 9 shouldn't be in the bracket. 2 cos x plus 9. Okay, the lowest value should be the lowest value on the outside function, right? Because the outside function is always rising, the lowest value from your inside function is going to be the lowest value on your outside function. And it's unlike the decreasing one we did before where it was flipped, right? The highest value on f is going to become the highest value on g. Okay? So let's think now, what is the highest and lowest value of f? Well, the highest value would occur at 0, 11, right? Thinking about this function as a cos function, right? So if you plug in 0, that's the highest. Cos starts at its maximum, right? So you get 0 times, cos of 0 is 1. 2 times 1 plus 9 is 11. Okay, so that would be the highest value on f. The lowest value would occur half a period later at pi, and you would find the y value was 7 at that point. Now let's plug these things in to g of x. So if we remember we're plugging in the 11, not the 0. Because remember, the 0 goes into f, and the result goes into g, right? So try not to. It's weird because the y value is suddenly becoming the x value, but you got to think about why that is, right? The x value here becomes a y value here, and then the x value here becomes a y value there, right? And then in this part in the middle, the first function's y value is the second function's x value, right? It's a bit confusing. In any case, when we get to 5x minus 40, right, which is what the other function is supposed to do, 11 times 5 is 55, take away 40 is 15, so that should be the highest value we're going to get. Meanwhile, 7 times 5, right, is 35, take away 40 is equal to negative 5, and that should be our min. This means that negative 5 is less than equal to y, is less than equal to 15, should be the range of the function when we do it in the reverse order. Okay, so again, this is my drawing of f of g of x. What if I drew g of f of x, right? And this, of course, looks quite different. So let's just bring it back. And my theory was it should be capped at 15 on the top, and it should be capped at negative 5 on the bottom, which you can see is a pretty good model, right? It captures it perfectly. So let me summarize this by just going over the 3 big points of what we talked about here. Okay, number 1, when you are doing a combined function, one function takes the variable, the other function takes the first function as its variable. So the variable itself is a function. Okay, in my situation, volume is a function of radius, and radius is a function of time. Right? So it's almost like a knock-on effect, right? You do one function and then you turn around and plug that into another. That's super important. And I find drawing these diagrams of like x goes into g and g goes into f as being useful. Now, the second thing to understand is all about the domain. For the domain of a composite function, the restrictions on the inside have to be kept exactly. You just find them the way you normally would and restrict them, and nothing can change that. However, the restrictions on the outside are more complicated. Instead of saying that the outside, again, let's just do quickly f of g of x, and let's say that the domain of f was x greater than 3, just for example, then in this question, it is the case that g of x has to be greater than 3. So you set g to f's restrictions. Okay, that's a really important idea for getting these ones right. Okay, so that's idea number 2. Idea number 3 is about the range. The range is a very difficult question, and I'm not going to be looking for anything much more than what we're doing here. It may be even easier than what we're doing here. And what the key to understanding the range is to think about is the outside function always rising or always falling? And then is the inside function when is it at its lowest and when is it at its highest. Now, of course, there can be other examples of this, right? There can be like the outside function has a max or min and the inside function doesn't, or something like this, right? And that's what happened with our cos question over here. And what we did there is we just said, okay, well, the outside function has maxes and mins. Does the inside function cause them all to get hit? And that's really all you've got to ask. So take it slow, try these ones, ask questions about them, right? Remember, it's a complex topic. It's very good to challenge yourself and try it, but like testing wise, I think anything like this, or maybe the one there, the other one in the middle of the page with the exponential and the quadratic, like those are really as tough as I would consider. Okay, so give them a try, and reach out if you have any questions, and hopefully you found this helpful in terms of making some connections between domain and range of composite functions.